welcome to this course in Noise Control and Mechanical Systems with me, Professor Sneha Singh from IIT Roorkee. And in today's lecture, we will discuss about porous-fibrous sound absorbers. So far we have begun our discussion on what is passive noise control, and in passive noise control usually materials are used for path modification. So, the various kind of acoustic materials that are used up, and then one type of acoustic material could be either be absorber acoustic materials, or they could be barrier materials we had. So, in today's class, last class we started our discussion on what are sound absorbers and what are the performance metrics such as the sound absorption coefficient and the noise reduction coefficient, which are used to measure how much of the acoustic energy that is incident of them is getting absorbed and dissipated within the material. So, in today's class we will see the first type of absorber, which is the porous fibrous sound absorber. Okay. So, just the introduction to what these absorbers are, what are they made of, their sound dissipation mechanisms, what are the factors that affect their sound absorption, and some of the advantages and the limitations of using these sound absorbers. So, usually as the name suggests, porous fibrous, so which means that they are a class of materials that they usually contain thin fibers that are loosely bonded, or they contain solid structures with interconnecting pores. Okay? And because of these are either made of loosely bonded fibers, or they are made up of the solid structures with a lot of interconnecting pores. So, that is why in their surface, whenever a sound wave is incident on it, there is a lot of gaps, and there is a lot of pores or openings available on the exposed surface through which whatever sound wave is being incident, it has a way to pass into the material. Okay. So, the material has got the fibers or the solid structure and a lot of gaps, air gaps or openings in the form of the gaps between the fibers or these interconnecting pores. So, that is why any such porous medium or porous fibrous medium will have two phases. First would be the solid phase, also called as the frame or the matrix, and then you have the fluid phase, that is the air, which is the most common acoustic medium or any other acoustic medium. Okay. So, these are the two phases, it is a two phase material. So, this shows a typical picture of an untreated glass fiber. So, these glass fibers that are manufactured, they are supposedly very good sound absorbers, and this is a magnified SEM image of this untreated glass fibers, and as you can see there, these are lot of fibers are there, but they are quite loosely held together, and you have a lot of air space in between these fibers. Okay, a lot of ways through which air can pass through them. And this is even a further magnified view which shows these are the fibers and these are the air spaces, which I can represent it with this particular thing. So, these are those air spaces in between the fibers. So, as you can see, both air and the solid phase is available, and it is due to these so many air space that is available, or the air voids that are available in these loosely bonded fibers, and the sound wave gets a way or a pathway to pass through. So, this is the example of a fibrous sound absorber. So, porous fibrous means combination of both, either porous or fibrous. They are studied together because they both have similar sound dissipation mechanism and similar kind of absorption properties. So, again the previous one was an untreated glass fiber. This is a resinated glass fiber, which means that to give more more sort of sturdiness to the structure, because otherwise loosely bonded material or loose fibers, you cannot use it as a proper structure or a wall or a lining. So, in order for it to have some shape to hold on, sometimes you add resins or other kind of adhesives that can be used to bond these fibers, so that the material can be woven up or the material can be formed into a layer of sturdy material, right. So, these fibers can make up a layer of sturdy material. So, once resinated glass fibers also, you see that some of the fibers are getting bonded up together here, but still there are some air spaces through which air can pass through. Then the other kind of porous fibrous absorbers, we have the porous sound absorbers, like you can see these various kind of foams that are available. Okay. So, in the market if you go, you have a closed cell foam, which is the foam, it is still a foam, but the outside of it you would not find so many holes or openings or pores on the outside surface. Okay. The outside surface would be closed and the inside would be a porous foam. Okay. So, that is called as the closed cell foam, and that is usually made, for example, in your sofa coverings, if you want to make the sofa sets and various other things, especially outdoor using kind of purposes, there you have these closed cell foams, so that water or other dust particle cannot enter into the material. So, the surface is closed from the outside, but in the inside you have pores. But those closed cell foams, they are not acoustic materials or they are not good absorbers, because for a good absorber you need a way for the sound waves to enter the materials, and that is why open cell foams, they are used as sound absorbing materials. This shows up a magnified SEM image of an open cell polyurethane foam. This is a small, this is the SEM view, this is a regular view in which you can see these various foams, and in the surface itself you see a lot of grainy texture. So, a lot of pores are available on the surface itself. Okay. So, open cell means pores are available on the surface and they connect one end to another end of the surface to the other end. Okay. So, open cell foams, they act as absorbers because they have so many such all these grainy textures or pores on the exposed surface. So, they provide the means for sound waves to enter inside the material and then the sound waves get dissipated. Okay. So, let us study what is the dissipation mechanism when such fibrous and porous materials are being used. So, now you know that how the sound wave enters, because these materials, be it fibrous or porous materials, they have a lot of pores or lot of voids, air gaps in their exposed surface itself. Okay. It is not a rigid surface, but it has got a lot of grainy texture, a lot of pores and lot of voids through which the sound wave is entering into the material. Okay. So, now what happens, what leads to the dissipation? So, once the reflection gets minimized because it allows most of the sound waves to enter inside it, but what happens inside, so that this energy gets dissipated and the transmission at the other end could also be reduced. So, what happens? Let us see step by step. So, majority of the sound energy that is being incident, it is able to enter inside this material through the various numerous pores and the openings that are available on the surface, and that is why open cell foam acts as an absorber, not the closed cell foam. So, once the sound energy incident is able to enter inside the material, then upon entering, they pass through a series of such tortuous tunnel like interconnecting pathways, because of these various kind of randomly arranged fibers or various kind of randomly interconnecting ports, a lot of a series of tortuous tunnel like path they have to go through. And while they are passing through this, most of their energy gets loosed as heat, okay, because of whatever is the internal resistance they are facing within the material, and hence the energy gets lost, and by the time they reach the other end, so from here till here, this transmission also drops. What is the internal resistance that is faced? What is leading to the loss of the sound energy as heat? The two most common mechanism or the two most common phenomenon that lead to the dissipation of sound energy in this material is the viscous shear and the friction. And experimental studies and empirical studies, they have shown that these are the most contributing phenomenon. They are the two most common, they have the majority of they have the most influence in dissipating the sound energy, although there are other phenomenon as well, but they are the most influencing one. So, viscous shear, what happens when the incident wave, it's incident. So, sound wave is what? It is like sound wave is simply the longitudinal fluctuation of the air particles. Okay. So, once a sound wave is entering into the material and going through this tortuous porous kind of tunnels, these longitudinal sort of fluctuations are happening, then energy gets lost due to the viscous shear or the drag that is faced by the air vibrating or oscillating air molecules against the boundary walls of the pore. So, the concept is very similar. Like for example, suppose you have some rigid wall structure and a fluid such as air is flowing through this rigid wall structure. So, near the wall it is going to face viscous resistance, okay, which is simply the resistance to the flow of a fluid along the solid wall, near the solid wall. So, whenever the sound waves are flowing, they are going to face a resistance due to this viscosity of the pores or the solid structure, and that will resist the flow of air particles. And here the air particles are longitudinal oscillations flowing back and forth through these various air channels like this, okay. And because there are some numerous such channels, you have numerous such small channels, and hence the viscous resistance becomes important and dominant. In the same way, you have when the sound waves, they are moving through the structure, they can cause the solid structure or the fibers to vibrate and rub against each other, and some of the energy can also be lost due to the friction because of the fibers rubbing against one another. So, you can see it here, in the first case we have the viscous losses happening. So, suppose these are the various fibers or various solid structures. So, these circles are the solid medium of that porous fibrous material, all of this are the solid medium, solid phase, and this one over here, let us say, is the air phase, okay. So, the air molecules, they are vibrating and moving through this structure, but whenever they are passing near the walls of the solid structure, they are facing viscous resistance whenever crossing through these walls, and there are a lot of such walls because you have a lot of thin fibers, or you have lot of these interconnecting tunnel like pores. So, the chances of the fluid flow through these various solid structure is a lot. So, they face a significant amount of viscous losses while when the air molecules, they are fluctuating back and forth near the walls of these solid frame or the solid fibers, okay. In the same way, here what happens when the sound waves, they are moving and these fibers, they are loosely bonded together, then because of the movement, fluctuating movement of the sound wave, sometimes the fibers also they are set into vibrating motions, they are rubbing against each other and frictional losses are happening here. Some other phenomenon that takes place. So, although viscous shear and friction, they have a greater impact on reducing the sound energy, some of the other phenomenon are scattering and the structural vibration. So, what happens in scattering? Some energy is lost whenever the sound wave is hitting the bends in the fiber or any kind of bends in the porous matrix structure, then scattering happens. Now, we know that here whatever is our porous material, the pathway is not straight. It is not like the sound wave is going through a straight pathway. These are various tortuous like pathways, like for example, here also it is not like the sound wave is going straight. If I had to create a pathway for the sound wave, okay. So, it might not be going straight, it might be taking a tortuous kind of a pathway, not a haphazard kind of a pathway, okay, like this. So, not straight but haphazard. So, whenever they are going and they are hitting some material, some scattering is happening here, and again they are going, they are hitting some material, again some scattering is happening. So, the waves while passing through, whenever they encounter any kind of bends or any kind of sudden obstruction in the form of the fibers or the solid frame, they undergo scattering, and there also some energy gets lost within the material. Then the structural vibration, the sound waves, they are trying to because they are longitudinal fluctuations of air particles and they are passing through a solid frame like structure. Then they try to compress and expand the frame, and if the frame has got a sufficiently high bulk modulus, then some of the work would be done by the sound energy in trying to compress or expand the frame, okay, and that will also use up the sound energy and dissipation will happen. But these phenomenon are usually rare, for that you need that kind of a frame, but viscous shear and friction are more contributing towards the absorption of the sound. Now, what are the factors which affect the sound absorption coefficient in these materials? SSE depends on, first of all, the incident frequency, then the thickness of the material composition, the surface treatment and the method of mounting of these materials. So, let us see first incident frequency and material composition, how are they affecting? Okay. So, here I have a diagram from my own paper which we published in 2018, where we were comparing the sound absorption coefficient of various common porous fibrous absorbers, and we had jute felt, waste cotton, coconut coir, flax, wood curls and rice straw. So, various kind of natural plant based porous fibrous absorbing materials were made and their SSE was compared. You can see that with frequency the values definitely change, and what you observe is that typically at a frequency below 1000 Hertz, SSE is low, and as the frequency increases, SSE increases and then becomes constant almost like that. So, the variation you can observe with frequency. At low frequencies, the SSE is typically low in value, So, frequency is low, SSE is typically low in value, and as the frequency increases, SSE increases and then almost becomes constant, approaching 1, because SSE cannot be greater than 1. So, finally it increases and reaches up to 1 and becomes constant, till it becomes 1. So, like that a typical pattern you can observe. Sometimes you can also observe some dips. So, what you see is that there is a variation with respect to frequency, and it also depends on the type of material you are using. For example, typically here it shows that the jute felt composite is having overall higher SSE compared to a material such as the coconut coir here. So, depending on how close, how you have made that particular composite, what kind of density of fibers you are using, the density of your fibrous material, the kind of resin treatment you are giving them, etc. So, based on how it is made up and overall built, the SSE is going to change, and at the same time with frequency also it is going to change, where typically SSE is low, very low, below 1000 Hertz. So, why this happens, why we are observing low sound absorption coefficient and the low frequencies? So, here you can think of it this way, whatever phenomenon, whatever sound dissipation phenomenon we observed, viscous shear, friction and all of that. So, here the more a sound wave is made to pass through, the more it resistance happens. Okay. So, as they are passing through this material, so they are facing all these resistance due to the viscosity and the frictional losses and all that, and they keep losing the energy as they go through the material. So, obviously, if the thickness of the material is more, they have to go through a long pathway, and per unit length they keep losing their dissipation, they keep losing their energy. So, suppose if the dissipation rate is roughly constant per unit length of the material they are covering, then as you increase the thickness of the material, what will happen? With increasing thickness, more and more energy will get dissipated till it reaches some optimum value, and then the thickness does not have an effect. In the same way, suppose we have got a typically low frequency, high frequency sound waves, which means that for these high frequency sound waves the wavelength is going to be small. So, which means that if the material thickness is constant, so that the amount of length they have to cover through the material is constant, but the high frequency waves are there. So, which means that the wavelength is small with respect to the material thickness. So, more number of wave cycles for that particular material thickness, and hence more is the dissipation, because crude way of saying this could be that, let us say I have got a certain thickness of a material and I am passing a very high frequency wave through it, and roughly 1 lakh wave cycles are passing through that material. So, a lot of waves overall are passing, a lot of wavelengths of that material is passing through, and lot of dissipation is happening, because for every fluctuation some kind of dissipation is happening. But if we have a low frequency wave, then instead of the 1,00,000 wave cycles, I just have 1,000 wave cycles passing through the same material. And so with so the fluctuation, the rate of fluctuation is low, and hence as they are passing through this material, the dissipation is also low. So the effective material, so here whatever the thickness of the material with respect to the wavelength of the wave becomes important, how thick the material is in comparison to the wavelength of the wave. Okay, if the material is very large compared to its wavelength, then more dissipation will be happening, because more number of wave cycles are passing through and having the losses happening there, okay, and vice versa like that. So here you can see with the same logic, as you increase the thickness, the SSE sort of goes up, because you are increasing the pathway of resistance, and with as they are passing through the material, their energy is getting lost continuously while passing through the material. So the more and more material they have to pass through, more energy gets dissipated till it reaches some optimum level, beyond which the thickness will not have that much effect. So this is the typical pattern that you would observe, with the increase in the thickness, usually the SSE will rise, and then after that, once it reaches a certain optimum level, the material thickness will not have that much effect. Okay. Then what is the effect of surface treatment on the sound absorber? So now you know that for the absorption to happen, the first thing these materials need to do is allow the waves to enter inside them. Only when the sound waves are able to enter into this medium, porous fibrous medium, they will undergo all these dissipation mechanisms, and the wave energy will get lost within the material as heat. So the transmission will be reduced, at the same time reflection will be reduced, because the waves are not reflecting back, but rather they are entering into the material. But if suppose you close up the pores, let us say you paint the surface of the material, or you smoothen the surface, which leads to the reduction in the pores or the air gaps at the surface, then what will happen? The material will slowly start behaving like a reflector instead of an absorber, because the waves are hitting the material, but now you have painted or varnished the surface. Now they no longer are getting any pathway or open pores through which they can enter inside. So say they simply reflect back. So once they reflect back, their absorption goes down. So such kind of surface treatment is definitely not encouraged, because it leads to the reduction in the absorption, So any kind of surface treatment that leads to covering up of these pores and the holes, it will make the absorption go drastically down. Then also the effect of mounting method, mounting method affects the absorption. What are the typical mounting methods? Typically, what you have is an absorber lining, and on top of it you install a acoustically transparent membrane. So in the last lecture I told you how is a typical sound absorbing treatment. What happens there? On the top of the material, sometimes you have an acoustically transparent membrane such as a mylar film. So what happens? It stops the entry of dust and the smoke particles, so that the pores do not get clogged and remain free, but it allows the sound waves to pass through. Okay. So that is why we have this protective layer of film on the top, so that dust and air particle, the dust and the smoke particles and impurities, that do not clog the pores, and only sound waves can pass through it. There are various such acoustically transparent films. And then you have the absorber followed by a backing, so that whatever sound transmission reduced or whatever, finally it reaches the backing and further reduction takes place, so that almost the transmission goes down even further, and that is why you have a barrier backing to make the transmission go down even further. The other kind of treatment is the bonded unbonded, where you have an air gap introduced. So you have a film at the exposed surface of the absorber, then you have some air gap, and so immediately following the absorber you do not have a barrier backing, but rather you have some air gap in between. Then you have unbonded bonded, where the exposed surface is not covered with a protective membrane, okay, but it has a barrier bonding at the back side. and unboarded, which means that there is an air gap at the exposed surface where the sound wave is incident, and there is also an air gap at the reflected end of the absorber. And depending on what kind of mounting conditions you are using, whether bonded, unbonded and so on, and what is the depth of air gap you are using, what is the kind of barrier backing you are using. So, depending on these conditions also the sound absorption coefficient changes. So, let us see a graph. What happens here, you have got a material with no air gap, directly a barrier backing, and now you have an air gap between the barrier backing. And what is happening is that when there was no air gap, the values at the low frequencies were low, but with the introduction of the air gap, some of the low frequency absorption has enhanced, but it has come at the cost of reduction of the SAC at the higher frequencies with the introduction of the air gap at the back of the. So, this is the condition of bonded, and bonded, unbonded. So, one case is where you do not have any air gap, this one, versus bonded, unbonded, where you have an air gap between the porous layer and the barrier at the back. Some air gap is there, which is 10 centimeters. In the same way, these are the 4 different graphs. What you have is, in all these graphs you just have a 1 millimeter of air gap. Okay. So, overall it is not affecting the thickness of the entire sound absorber you are creating out of the membrane, the porous material and the barrier backing. So, all of them combined together, the thickness is just increasing or decreasing by 1 millimeters when you are introducing an air gap. But what is happening because of it? Suppose it is bonded, it is giving you this kind of a peak. When you have an unbonded, bonded thing, then suddenly you have a much higher SAC value. And then when it is bonded, unbonded, which means an air gap which is behind the porous material before the barrier backing, again similar thing, what happens? The peak shift towards the lower frequencies. And then when you have unbonded, it is something like that here, higher peak again towards the lower frequencies. So, various kind of treatments can be seen, and you can see how tailoring the air gap either at the exposed surface or behind the porous material, how this mounting condition can change the SAC of that particular material. So, to summarize from whatever we have, typically mounting method does affect SAC, and if air gap is introduced, it is said to typically enhance the low frequency absorption, but this enhancement at the low frequencies can come at a cost of decrease in the absorption magnitude at the other higher frequency zones or at the other places where it was initially high. So, we know that in the porous material, one of the shortcomings is that SAC is below, SACs at low frequencies are usually very low. You can introduce air gap to make the situation slightly better, where with the air gap you can enhance the values of SAC at the lower frequencies, but then that will reduce the absorption coefficient elsewhere. Okay. So, these are the typical kind of absorption treatments, and let us see some of the advantages and the disadvantages of these kind of absorbers. So, they are very good for broad range high frequency absorption. So, if proper treatment is done and a material is made, so let us see these kind of values here. You would say that usually the absorption coefficient is quite high, it is almost above 0.8 in a large range beyond 1000 or 15,000 hertz till 4000 hertz or so on. So, for a large broad range you have got higher value of SAC that can be achieved. So, broad range high frequency absorption is possible. We do not have sharp peaks, but that are a broad range of consistently high values. Then we also have the opportunity of using the natural fibers such as jute, coir, etc., which use biodegradable, recyclable and abundantly available materials. And when you use these kind of things, then you can basically you can create the sound absorbing material which are biodegradable in nature, they are recyclable, environmentally friendly, they are also very abundantly available in nature, and that is why they are very low cost as well. All of this is sort of advantages with the porous fibrous absorbers, but obviously there would be some disadvantages, and as a noise control engineer then you have to decide based on what is your application, what is what is your application, whether they suit your application or not. So, what are the limitations we have? That they are not durable, which is their performance is dependent on the exposure of the pores and the openings on the surface. Okay, on the surface the pores and the openings must be there, but over time these pores, so suppose you do not have protective films or anything, and over time these pores, they are exposed to the air, they are bound to get clogged by the dust and the contaminants of the air, and with time the absorption is going to go down. So, they are not very durable and they are unclean again. If you are using loose fibers, then after a certain time the fibers they fall off from time to time, they can hamper whatever machinery you are using these materials in. So, they are not very clean, fibers are there which can fall off, or even if you are using porous structure, it can get damaged and the slowly it starts to fall off. Then timely maintenance and cleaning is definitely required, because because of the tendency of the pores and the openings to get clogged with persistent usage due to the contamination from the air. Whatever contaminants are present in the air, they can clog it. And the last kind of limitation is that they have poor absorption at low frequencies, typically below 1000 Hertz. So, suppose your application requires absorption at the mid frequency and the high frequency ranges. Okay. So, I think in that case the porous fibrous absorbers could be your best bet, they could be your best solution, because they would offer relatively good sound absorption coefficient over a broad range of mid and high frequencies, and you do not need to do any additional treatment. One thing you would just need to see is that they should be timely maintained and cleaned, but they would always be a low cost solution for you for mid and high frequency noise control. But if it is a low frequency or more targeted noise control, then you can think of other solutions for sound absorption. So, with this I would like to close this lecture. Thank you for listening.